Good morning, everyone. I'm Xuancong Wang, National University of Singapore. So today the topic I'm presenting on is combining punctuation and disfluency prediction, an empirical study. Here's an outline for my talk. I will begin with my introduction, followed by some previous work. Next, I will describe our baseline system. After that, I will talk about the three approaches which do both punctuation and disfluency prediction, namely the cascade approach, the rescoring approach, and the joint model approach. Finally, I will come to the discussion and conclusion. The motivation of this work is because the output from automatic speech recognition does not contain punctuations. Moreover, spontaneous speech contains disfluencies, which does not carry useful content information. Some literature study shows that natural conversations contains about 5 to 10% disfluency. For the switchboard corpus used in this work, the proportion of disfluency is about 15%. Therefore, as post-processing steps for speech recognitions, punctuation and disfluency prediction can improve downstream natural language processing tasks, such as machine translation, spoken language understanding, etc. Let me introduce to you about the two tasks. The task of punctuation prediction is to add punctuation symbols to unpunctuated text, such as the output from speech recognition systems. Punctuation prediction on long streams of words also achieve the purpose of sentence segmentation, and thus is more challenging. So this work deals with this more challenging task. In this example, how do you feel about the Vietnamese word? I saw that as well. The question mark also split the utterance into two sentences. The task of disfluency prediction is to predict words which are incorrectly spoken. For example, consider the following sentence. The speaker has initially spoken the wrong destination, Boston. After that, he paused and hint to make a correction using I mean. Finally, he spoke the correct destination, Denver. So the part to Boston, which is spoken by mistake and is to be corrected, is called the edit words. And the part I mean, which is inserted to hint for the corrections, is called filler words. And finally, we have the clean up sentence. I want a flight to Denver, which is what the speaker intends to say. In an application when we need both tasks, a natural question will arise is that which task we should do first. Consider the first sentence. If punctuation prediction is performed first, it might treat this utterance as three sentences. I am, I'm not going with you. If the three isolated sentences are passed into the disfluency prediction system, each one is legitimate on its own, and the disfluency will be missed. On the other hand, if disfluency prediction is performed first, certain repetition patterns and new sentence might give false alarms to punctuation prediction. So overall, there might be some features. For example, in here, I am. This is a repetition feature. Yeah. So the disfluency prediction system might confuse that this might be a disfluency. So that's why there might be some features causing confusion between punctuation prediction and disfluency prediction. So we need to study their relationships. Now comes to the previous work. On punctuation prediction, people have tried neural networks, log linear models such as maximum entropy model, linear chain, and dynamic CRFs, and shift-reduced algorithms such as transition-based parsing. On disfluency prediction, people have tried noisy channel model, phrase-based machine translation approach, HMM, max and CRF, etc. And weighted max margin Markov networks and combination approaches such as Bing search decoder. There are also some works that deal with both tasks. For example, Liu et al. And Byron et al. Has treated them as separate tasks. Stoke et al. Has mixed sentence boundary labels with disfluency labels. Kim has done a joint sentence unit and interruption point prediction in which edit and filler regions are derived from predicted interruption points using a rule-based system as a separate step. However, they have not studied on combining the two tasks as one joint prediction task. So in this work, we mainly study the interaction between the two tasks to show that combining the two tasks can give better performance. And we also compare various methods of doing the combination. So in this work, we use the switchboard corpus, LDC 98042, with the same training, develop, and test split as previous work by Qian and Liu and Johnson Shanak. Pause duration features are extracted from the corresponding speech corpus, LDC 97S62, after running force alignment. This table shows some statistics of corpus we have used. As you can see that the proportion of different labels in the training set is quite similar to development and test set. However, since the proportion of exclamation marks and the incomplete sentence units is too small, they are mapped to periods for both training and testing. The baseline model are trained using max margin Markov network, or M3N. To make comparisons consistent, we use the same features in all our experiments, except for the soft cascade, which I will talk about later on. The basic features are the same as Qian and Liu's work. The additional features we use are the word pair features. This feature can capture word pairs, which can potentially indicate a repair. For example, words something is, or the speaker may have spoken any words in between. And it's very difficult for standard n-gram features to capture all variations. And the n-gram score features, they provide language model information on the lexical continuity or discontinuity. And also the pause duration features is obtained by running Viterbi force alignment. Both n-gram score feature and the pause duration features are continuous features, so they are quantized into 10 discrete bins for use as features. In this work, for punctuation prediction, we use 4 labels: comma, period, Q mark for question mark, and none for no punctuation. For disfluency prediction, we use 3 labels: E for edit word, F filler word, O otherwise fluent. Since the proportion of disfluent labels and punctuation labels is much less than that of the neutral labels, we use the standard F1 measure, which is the same as previous work. Here's the result for the baseline system scores. So comparing the second and third row shows that joint edit and filler prediction works better than edit prediction alone. Comparing third and fourth row shows that joining sentences together has a major impact on the accuracy of disfluency predictions, as the number drops from 84.7 to 79.2. Comparing fourth and fifth row, precision recall balancing gives about 1% improvement on the F1 on disfluency prediction, but it doesn't affect punctuation prediction much. Comparing the last 2 rows shows the effect of click order, as we are not using the BIES, begin inside and single labeling scheme. Now let's combining the 2 tasks. The cascade approach means doing one task followed by the other. We have compared hard cascade with soft cascade. For the hard cascade, we apply the prediction results from the first step to re-extract features for the second step. For example, for punctuation PO to DF, we predict punctuations first. Then we split the input utterance into individual sentences according to the sentence end punctuations. So in this case, it becomes 2 sentences, and then pass the individual 2 sentences into the second step, disfluency prediction. Similarly, from this DF to PO, we predict disfluency first, then remove the disfluent words, and pass the clean up sentence into the second step, punctuation prediction. For the soft cascade approach, we use the labels from the first step as additional features for the second step. For example, from PO to DF, the labels are non-period, comma, and Q mark. From DF to PO, the labels are O, E, and F. In our implementation, the feature templates, in our implementation of the feature templates, the first step predicts label of the previous word, the current word, and the next word are used as a feature for the second step. So here's the result. It's quite worth noticing that if the output from the first step is all correct, which is the cheated case as indicated in the bracket, then hard cascade actually performs better than the soft cascade. However, otherwise, hard cascade performs worse than soft cascade. Yeah. So this could be due to that by applying the outcome from the first step, different features will be extracted in the second step because of the sentence boundary, deleted, added, and filler words. So hard cascade actually propagate more information from the first step into the second step, and that's why it's more sensitive to the errors in the first step. Now we come to the rescoring approach. The standard formula for doing the cascade is the probability of the first step prediction given the input times the probability of the second step prediction given the first step output and the input. One problem with the cascade approach is that it only passes one best output to the second step. So this might cause significant error propagation. A straight-away solution is to propagate multiple hypotheses instead of one best hypothesis. It's also called rescoring. In this work, since we have 4 models from the soft cascade approach in both directions, we have made it more general by rescoring all the 4 models instead of just 2 models. And the weights are optimized using MERT, minimum error rate training, on the development set. So our method is as follows. Firstly, we predict punctuation and generate n-best PO hypothesis. Then for each one in the n-best PO hypothesis, we generate n-best DF hypothesis using the second step model from soft cascade. After that, we do the same thing for DF to PO, so that we get in total 2 n-squared best joint hypotheses. And lastly, we do the log linear rescoring using scores from all the 4 models. From the results, we can see that as the n-best n increases, the oracle performance increases, which is shown in the bracket, and this is as expected. However, overall, there's no significant improvement using this approach if you compare with the soft cascade. One reason might be due to that, although we are combining 4 models, these 4 models are actually trained using the same features. So there's significant information and knowledge overlap among these 4 models, and that's why combining them does not introduce much new information for this task. So previously, both the cascade and the rescoring approach involves combination of several models. Since these models are trained separately, there's a lack of global optimization if we consider both tasks as one joint task. So in machine learning, there's joint prediction models which can predict multiple levels of labels simultaneously, as their model training involves global optimization of all parameters. So in this work, we compare 3 joint learning approaches. For mixed label LCRF, we split the neutral disfluency label O into punctuation labels so that we do not care about the punctuation label for disfluent words. And the model is still LCRF. For the cross-product LCRF, we compose the 3 disfluency labels with the 4 punctuation labels so that we have in total 12 labels. For the 2-layer factorial CRF, we use the first layer to predict the 3 disfluency labels and the second layer to predict the 4 punctuation labels. From the results, we can see that mixed label LCIF performs about the same as soft cascade. The 0.3% is not statistically significant. However, the overall performance of the cross-product LCIF and the two-layer FCIF however, the overall performance of the cross-product LCIF is better than soft cascade. You need to take a look at both the F1 on PU and the DF. The performance balance between DF and the PU is slightly different between cross-product LCIF and the two-layer FCIF, but their overall performance is not statistically significant. Throughout all the experiments, we have found that the concept of label granularity is very effective in explaining the differences in various experiments. Firstly, joint edit and filler prediction performs better than edit prediction alone. This is because joint edit and filler prediction distinguish between filler and fluent, although they are both non-edit words. However, edit prediction alone does not distinguish. Secondly, mixed label LCIF perform better than isolated LCIF because mixed label LCIF further splits the neutral label O into the 4 punctuation labels. Thirdly, both cross-product LCIF and two-layer FCIF perform better than mixed label LCIF because they distinguish between the different punctuation labels for disfluent words as well, and thus they have better label resolution. So the key idea is that during training, we may want to divide the labels into finer subclasses to let the model learn more information. And then during testing, we merge the labels for evaluation. In conclusion, punctuation prediction and disfluency prediction do influence each other, and the prediction outcome in one task can provide useful information that helps to improve the other task. Therefore, the various methods linking the two tasks all perform better than the isolated prediction. Secondly, for the cascade approach, we show that soft cascade is less sensitive to prediction errors in the first step, and that performs better than hard cascade. In other words, passing the predicted label as a feature into the second step is better than splitting the sentences or removing disfluent words according to the first step output. Overall, the two-layer FCRF and the cross-product LCRF perform slightly better than the mixed label LCRF and the soft cascade approach. This suggests that modeling at a finer label granularity is potentially beneficial. However, joint modeling might lead to a higher model complexity if higher order features are to be used. So that comes to the end of my presentation. Thank you very much.
So there was plenty of Q&A questions. So maybe let me get started. So about the rescoring approach.
Yeah.
When you deal with invest lists, one question is how efficient is it? Right? Or generally, across all of the different approaches, if you want to plug this into a real-time system, speech recognition, and then you have some output you want to perform the punctuation recovery and the disfluency detection, and then pass it on, let's say, to translation system. So, I mean, the results, they are all very close. So from a practical point of view, which one would you recommend?
Soft cascade.
Soft cascade.
Yes.
So this is the fastest processing?
This is overall, if you consider both the performance as well as the efficiency, as well as the space, the model size, and everything. Overall, this one is most cost efficient one. Yeah. Although it's not it does not have the highest performance. Its performance is slightly lower than the joint model approach. Yeah.
So actually in this table, the invested size was then for both the restoration of the punctuation and for detecting the disfluency.
Yes.
So did you experiment with, maybe one would give you more gain, increasing one invested versus the other one?
Yes, I have tried, but the result is still kind of fluctuating around. Yeah. Yeah. So the only thing that maintains consistent is the oracle scores, which is increasing. Yeah. But the practical scores it doesn't improve much. Yeah.
Okay, so if you don't have more questions, let them speak again.